Okay, so this is gonna be our last lecture, virtual and even in person. Monday is gonna be a review day. We're gonna go over the practice problems for the final, and I guess just address any questions that anyone has. So in this last lecture, we're gonna look at, we're gonna go through, we're gonna learn the law of sines and the law of cosines. Before I do that, though, I want to go back to section 6.3. There's one thing I didn't cover that we're gonna sort of need for this. We're going to need for the to do in order to prove or derive the law of sines or cosines. So we're going to talk about area of triangle. So we know how to take the area of say a right triangle. That's just 1/2 base times height. And that really comes about because we have um a right triangle, but we want to be able to find the area of more general triangles. Ones that are not necessarily right triangles. And in deriving a formula for the such triangles, we're actually gonna use the fact that we know the area of a right triangle or properties of right triangles to get that. So there are gonna be two cases. So um suppose we have a triangle. I'm gonna draw some pictures in a moment, but just some setup. So we have a triangle with one of the angles equal to theta. So theta is just some number. And this is actually going to give us two cases. So we have two cases to consider. Two cases to consider. And the first one is that theta is an acute angle, or theta is obtuse. So let's deal with the theta is acute first and derive the formula for the area of a triangle. So when you have theta is acute, you could have a triangle that say looks. Oh, let me see if I can try my best to draw this. You could have something that looks like, say, this. And this angle right here with theta, this will be the acute angle right here. And so let's label some of these sides. So we have A and B. Now what we're going to do is we're going to form a right triangle inside this triangle. So we're going to take this vertex right here, and we're going to drop down a perpendicular line right here. And this will form a right triangle. So this is going to have this length of this perpendicular line, or the perpendicular line segment going through this vertex and is perpendicular to the base A will have a length of h, this segment right here. And if that's the case, um, then we can actually figure out. So first of all, area, as I said, is going to be, let's say, just call it area, which we'll denote by A, is going to be equal to 1/2 base times, oops. All right, hopefully this works. Base times height, height h. And we don't want to really, we want to express the area in terms of A, B, and theta, not h, this height h. So, first of all, the base is going to be A, and then the height is just going to be h. So what we want to do is want to write h in terms, somehow in terms, we want to eliminate h Because what we're given is A, B, and theta. That's like the data that we're given, basically. And we want to be able to compute the area from that data, given data. We want to write H in terms of B and theta, and possibly A. For all we know, maybe A is involved in the formula for H. It's going to turn out that A won't be, and which is a nice feature. So what we have here is, as I said, we have this right triangle. We just focus on this, and we can use our trig functions to express H in terms of the given data. So for example, we could say that sine theta, and sine theta is the opposite divided by hypotenuse. In this case, B is going to be the hypotenuse of this right triangle we formed. So we have is B, sorry, it's opposite. We had too many windows open. I forgot to close these windows. All right, so it's H. All right, hold on. Let me stop my share so I can close these windows. All right, hopefully that helped. So let me share my screen again. So now if we look at this triangle here, so imagine we're standing at this vertex right here, and then we want to compute sine of the theta. Well, sine of theta is going to be the opposite sides of the length of the opposite side, which is h, divided by the length of the hypotenuse, which is b. So sine of theta is going to be h over b, and then of course we can easily solve for h in terms of theta and b. So it's h is going to be b times sine theta. And then that implies, so now h is can be written in terms of b and theta. So now we can write area completely in terms of the given information. So it's going to be 1/2 a times h, but h is b times sine theta. So this is a way of computing the area of a triangle if all you're given is this side a, b, and theta. So that handles the acute case. So now we need to consider b is obtuse. So that and then that will consider by doing that we will have proved we have derived a formula for any triangle. Because that's it. Those are the only possibilities that a is that the given angle is acute or it is obtuse. So now in this case the triangle might look something like the following. No, don't want it that sharp. Um, So the triangle might look like something like the following. Let's try it a little bit differently. All right, and so let's say that this is the obtuse angle that we're given. And here's A and here's B. So A is theta is the inscribed angle between these two sides. So it's the same sort of setup. We have this theta right here is this inscribed angle between these two sides whose lengths are known. So again, where'd it go? Okay, here we go. So again, we're given this angle theta, and it's inscribed between these two angles, or two sides whose lengths are known. So it's the same setup. And so again, we're gonna have area of the triangle is gonna be 1/2 base times height. Oops, I'm writing the word out. I don't need to write the word out. Write the symbol out. So it's my computer's still, I closed all the tabs, but my computer's still catching up, I guess. Times height. So this is the same general formula, but now we we don't quite, it's not quite clear how to get the height in this case. But we can do the same sort of trick we did in the other one, was to form a right triangle from the given triangle. And this is how we're going to do it. We're gonna again take a vertex. So in this case, we're going to take this vertex, and we have we can imagine that this side A right here, we can extend out this out as a line going up to infinity. This ray, and then this will form a line, and we can form a line perpendicular to it going through this vertex right here. So we'll drop that down a perpendicular line. And so because these are perpendicular, this angle right here necessarily is equal to is a 90-degree angle. So now we have this other so let's try to figure out the rest of this triangle. First of all, we have this is the height h. This will be the height of the whole triangle. And we have this other angle right here. We'll call it like beta, I guess. I don't know. Maybe we can figure out beta, what beta is. And we can actually, because we know that the these are complementary angles, I think they call them. They're they share a same ray. So I guess what that means then is that we know, for example, that the sum of these angles has to be 180 degrees, and then that means we can write beta completely in terms of theta. So now what we have is we have this triangle right here. So let's replace now beta with the actual angle. We know we can write it as 180 minus theta. So now let's imagine we're standing here. Now we're no longer standing at this vertex. We're standing here, and we want to compute this um, based on the these angle and these sides. So we can do that. So we are sorry, we can write, we want to, and the goal is to write again, write h in terms of what's known. We know a, b, and theta. So sine of 180 degrees minus theta is going to be equal to it's going to be equal to the opposite. So again, that's h divided by the hypotenuse. And again, b is going to be our hypotenuse. It's going to be b over h. And then this is going to imply that um, h is going to be equal to b times sine of 180 degrees minus theta. But again, these are like, I guess you call them complementary angles, or they are, I guess you would say that theta is the reference angle of this right here. Or no, this would be the reference angle. This right here, this is the smaller angle, right? That's what reference angle is. It's the smallest two angles. So it turns out that sine of this reference or complementary angle is just going to be sine of theta. So this is just a fact. And now we can write the area again as 1/2 times base, which is a, times the height, which is now we know b times sine theta. So again, we get that the area can be expressed using the same formula. So in other words, the conclusion is that whether theta is acute or obtuse, the area is always given by 1/2 AB times sine theta, which is kind of nice actually, because if you're like you would say a priori, that is like before you actually go through the proof. A priori means like prior to experience. A priori, there's no reason to think that the formula is going to be the same, whether theta is acute or obtuse. You know, you have these two cases. So for all you know, you might have to have two formulas, which would be really annoying. You would need these two different formulas depending upon which case you're in. But theta is acute or obtuse. But it turns out that you don't need that. This is going to be the same formula in either case, which is a really nice fact about reality and about nature, I guess. All right, um, so let's just summarize this kind of as a theorem then, I guess. And we're going to use this in deriving the law of sine and cosines. So we'll say the area A of a triangle, oops, with sides A and B with, I guess they're using the word included, but I think you can say it. I think the right word is inscribed also. So I'll say with inscribed, oops, but I think the idea is clear what's meant. Or included angle theta is, so the area is given by the following, the formula we just deduced or derived. So it's going to be 1/2 AB times sine theta. All right, so now let's go to the law of sines and cosines. So basically, if you have a right triangle, so this is 6.5 and 6.6 on law of sines and cosines. There'll probably be a question like this on the final. There usually is, with you about find the law of sines or cosines. And there's in the bonus assignment I posted, there's some problems on the law of sines and cosines. So if you don't do if you're gonna do any problems in the bonus, definitely do those problems on the law of sines and cosines. Those will help with the final. Um, so yeah, just want to say that, point that out. So what we want to do is we want to develop some formulas to so-called quote unquote solve triangles, and that just means you're given some data about the triangle, say some lengths of sides or maybe some angles, and you wanted to figure out the rest of the sides and angles given that small amount of information. You want to like basically complete these triangles in a sense. And there's going to be multiple cases, so I'm going to just pull the book up here for a moment. And depending on which case you're in, you're going to need the law of sines or the cosines. One's going to be more helpful. I think that the law of cosines actually always works. Don't quote me. I it's been a while since I taught this, so I don't remember all the details. I think law of cosines always works, but law of sines is a bit easier to work with. So if you can use the law of sines, use it. Um, so we want to solve a triangle, and we want to like, so there's multiple cases we have to consider. There's one case that we're not going to consider, and that's this case right here. Not in the right. Oops. Okay, not using the right PDF viewer. All right. So there's this case we're going to consider. It's right here in this sentence. That is if we know all three angles but no sides. And the reason why we're not going to consider this case is because that, as it says, it can't be uniquely determined. The triangle, because if I give you a triangle and say you only know the angles, imagine I give you a triangle and I give you the measure of the three angles in it, and the question is, can you determine the lengths of the sides? The answer is no, you can't uniquely determine. Um, and the reason why is there are many triangles with the same three angles. Basically, if I give you one triangle with the angles that are given, I can basically if I stretch all of the sides of that triangle by the same amount, that'll give me a completely different triangle with the same angles. So try to visualize that in your head. If all you're given is the three angles, you can't uniquely determine because the triangle, the lengths of the sides, because there are going to be many triangles. Um, they're going to be what they are all equivalent though, in the sense that they're similar. There's this notion of similarity of triangles, and it basically has to do with the fact that all the sides are proportional. Um, so you can imagine just a triangle and you can blow it up as big as you want. And it will still have the same three angles as long as you do if you, as long as you blow up the sides of the triangle by the same proportion. So the cases we are going to consider though are, for example, angle side angle or side angle angle. So in other words, I give you one side and two angles, and that has these two sub cases. And if I give you that just that much information about the triangle, one a side angle, or side angle angle, you can actually determine the rest of the triangle from that using the law of sides. The other case is going to be side angle. So and then there's going to be side angle side, and then there's going to be the case where you have all three sides are given, and then that all in all these cases you're going to have a unique or mostly unique. Maybe you'll have just two possible. There's going to be this notion of ambiguous case. I'm not going to go through it actually. I don't. I think it's kind of just distraction at this point, and I don't think there's going to be a problem like that on the final at all. Where it will turn out that I'll give you some data, and there are actually two possible triangles, which is more manageable. If I just give you three triangle, if I give you three angles, there are going to be an infinite number of triangles having those three angles a part of the triangle. But in some of these cases, there's only two possible triangles, so that's a bit more manageable. So what this means, like angle side angle, it means that, for example, you're given, you can see it, you can see what information you're given right here. You're given this angle here, and then you're given this side, and then you, from there, you want to determine the lengths of these dotted lines. So that's kind of what that abbreviation means. It means that you have this side, and it is part of the two angles of the other triangle. So for example, this wouldn't be side angle side. So like suppose if I give you this side right here, and then this angle, and then this angle, that wouldn't fall under this category here of angle side angle. And then the next thing, oh, this is a mess. The next one is side angle. And so you're given two sides that share the same vertex, you can see. And then one of the angles is associated to one of the given sides, you can see right there. So you're given this side right here, and then this side, and then this angle. And then the other case is side angle side. So you're given these two sides, and then you're given the included or the inscribed angle. And then the last case is kind of obvious. You're given all three sides. So these are the kind of cases we're going to consider. So before we do this though, before we try to prove or try to look at examples determining that like determining the whole or solving for the triangle based on this limited data, let's prove the law of sines. So I'm going to state it formally, and then we're going to prove it. It's not that hard to prove though. So it's the law. Let's actually say theorem. This is wait, hold on, I'm going to say actually give this theorem a name. So this is law of sines. So in a triangle, did A, B, and C, and the capital A, B, and C denote angles in the triangle, whether and which may be known or unknown. It depends upon what data you're given. So in such a triangle, we have that the following equations hold. Oops, I didn't. So we have the sine of A over the length of the side A is equal to sine of angle B over length B is equal to sine of angle C over length C. So a pretty nice formula. It's easy to memorize. So let's prove it though. Let's prove it. And it's going to be based on the idea of calculating the area of a triangle. So let's write a triangle and give it some names. Let's label it. So what we have is, so we're gonna say this is, let's just call this angle A right here. This is called B, and this is called C. And then the side opposite to the angle will be denoted by, the length of it will be denoted by the lowercase. So this is gonna be length A, C, and B. So now what we're going to do is we're going to calculate the area in three different ways. And since we're calculating the area of just the same triangle, all these calculations should be equal. So I'm going to calculate the area with respect to this angle, and then this angle. Or I'll start with A actually. So so what we can say is that the area of this triangle can be computed in three different ways, but they are all equal. But they are all equal. So what we have then is, so for example, if we're standing at this, um, let's remember let's see, so let's try to be careful about this because we want to use this area formula right here. This area formula right here. So what you have is, how do you calculate this area based on this formula? Well, I give you an angle, right? And then you use the sides that form that angle, right? So on the one hand, so if I start at A, then I know that the area should be 1/2, right? B times C, right? B times C, because these two sides form the angle A. So B times C and then sine of A. And so and we're using A in this case, not theta. But now that let's count. So again, remember the area formula for the triangle is I give you an angle and I give you two sides where those two sides form that angle. So if we're calculating the area with respect to this angle, I need to use this side right here and this side. They form that angle. So the area on the one hand, so this is the area, can be computed in this way. But on the other hand, I can start at this vertex and then this angle right here at this vertex, and then I can use this side, but now I'm going to use this side right here because those are the two sides forming the angle. So on the other hand, the area is also given by 1/2 A times B sine of B. So this again is the area. It's the same area. We're calculating the area of the same triangle. So these are just different manifestations of the area. They're all the same though. And then finally, now I'm going to calculate the area with respect to this vertex or this angle. So in this case, the sides forming this angle are is this side and this side. So it's A and B. The sides A and B labeled A and B. So it's going to be 1/2 AB times sine of C. Now multiply. So we have like a triple of equations, right? These three quantities are all equal. We're going to multiply each equation or every side of the equation, which kind of doesn't make sense since we have like three equations. But hopefully you get the idea. We're going to multiply by 2 over A times B times C. And when you do that, what happens? Well, first of all, this 2 right here is going to cancel with this 1/2. It's going to cancel with this 1/2. It's going to cancel with this. So our 1/2 is going to go away. Now when we multiply A, and now when we divide each part of the equation, this triple of equations by A, B, and C, well, we have a B and C here, so those are going to cancel, just leaving the A. So we have sine A over A is equal to, Now we have this A, B, and C is going to cancel with the sorry, this is not quite right here. Um, so sine B. Oh, yes, I made a mistake. It should be A times C. All right, so now when we divide ABC into AC, what we have is sine of B, and the A and the C cancel just to leave the B in the denominator. And finally, when I divide ABC into AB, I just have C in the denominator, so I have sine of C over C. And that's the end of the proof. So not terrible. So we can get this law of sines by just considering computing the area in three different ways, which is kind of a odd proof. Some proofs are kind of odd like that. It's all a matter of perspective. It's like how you can leverage. Yeah, mathematics is really just about finding different ways of viewing the same object or the same number or the same quantity. So we have this number, we have this object, and we have this quantity area that we want to compute of this object, and there's just these three different perspectives, three different ways of computing it, and that has a lot of consequences. The fact that you can compute the area in many different ways. So this will allow you to deduce this formula here. So let's prove. Um, so let's all right, I'm actually going to need because I don't want to. There's this picture in this diagram, this picture I want to use. So let me stop sharing for a moment. I want to open it up in the proper PDF viewer. So I want to actually draw on the. Let's see. I want to draw on the PDF, the document itself. So let me open that up. All right. Let me share my screen again. Okay. All right. So hopefully you can see this. So here we go. So this is what we just proved. And so let's work through this example, read through it and work through it. So this is the formula we just proved. So we have a satellite is orbiting the Earth and it passes directly overhead at observation stations in Phoenix and LA at some distance apart. And at an instant when the satellite is above these two stations, its angle of elevation is simultaneously observed to be 60 degrees, Phoenix and 75 at Los Angeles. So how far is the satellite from the Los Angeles station? So here we have this picture right here. So here's the satellite in orbit, and then we have Los Angeles and Phoenix. And well, they're showing you the distance here. But we want to compute that using the law of sines. So, sorry, this is the distance that's known, 340 degrees. And this is the angle that they're observed at from these stations. So what we want to figure out is B. We want to figure out this distance B right here. So now we know these two angles. We're going to use a fact about triangles that the sum of the three angles has to be 180 degrees. So that allows us to figure out angle C. So you can see angle C is going to be 180 degrees minus the sum of the two angles. So it gives you a 45-degree angle. And now this is we don't need to use all three equations. Actually, two. There's two equations. I don't know. There are three different equations in the law of sines. We're just going to use the part involving B and the part involving C. So we have sine over B, sine of B over B, and then sine of C over C. And we just were given B, and we were able to figure out C based on this like fundamental fact about triangles. So now we know angle B is 60 degrees, and now we just determined that angle C is 45, and we know that the distance between these two stations is 340, and B is the unknown. So we're going to solve for that. So basically you can, I guess, yeah, I mean, when you solve for it, you're going to get that, but I mean, maybe I should do this step out right here. Why do we get this like that? So I guess the best way to do it is just invert the equation. So you kind of like take the reciprocal of both sides. So then you get um, b over sine 60 degrees over is the same thing as 340 degrees over sine of a 45-degree angle. And then you can multiply both sides by sine of 60. So that gives you that b is equal to 340 degrees times sine of 60 degrees over sine of 45-degree angle. And if you know your angles or if you know your unit circle, um, let's see, the sine of the 60-degree angle should be, I guess, so that should be, actually, that is going to be 1/2, I believe. And then the sine of a 45-degree angle is √2 over 2. So let me see if, let me plug it into my own calculator, see if I get the right numbers. So yeah, 340 divided by 1/2. Well, that should be easy to do in your head. And then, so yeah, so it's 170. And then divided by, let's see, I just want to check that I got the trig functions right. So it's going to be square root of 2. Nope, I did something wrong, it looks like. Let's see. I must have done. Oh, all right. I know the problem. Sine of 60 degrees is √3 over 2. So these twos cancel out. So then I have like 340 times √3 over √2. And that should be, when you get like an approximation, that should be right. So let's see. So it should be 340 times, and then in parentheses, we get root of 3 divided by 2. Yep. And I get approximately, yeah, 416. So I just use the fact that sine, just on the side, I want to write this out. Sine is the same thing. Sine of 60 degrees is √3 over 2, and then sine of 45-degree is angle is √2 over 2. And I guess you could just memorize that 60 degrees corresponds to that, 45 degrees corresponds to that. Or if you prefer the unit circle, which I do, you can just remember that 45-degree angle corresponds to pi over 4, and a 60-degree angle corresponds to um uh pi over 3, sorry. And it occurred to me the other day that so for me, like, I didn't care about math in school at all. So I don't even remember honestly what I learned about when I was in high school or whatever. It was only when I got that when I went to university, I started like learning math and I got interested in it. I learned trigonometry through the unit circle approach, and I was talking to someone and like they say that it's more common to learn it's more common to define the trig functions using triangles and learning SOHCAHTOA and all that nonsense. So it for me, the unit circle approach is more natural because that's how I learned trig functions. And it is mathematically more natural, actually. But what you probably you students are probably more used to seeing is the triangle approach and using that SOHCAHTOA mnemonic, which I don't use at all. So however you think, use your discretion in solving these problems. Use the method that is you learn and that you're most comfortable with. And like I said, it's probably more likely that the method you're more comfortable with is using triangles and um, using SOHCAHTOA mnemonic. But I do want to point out that mathematically, the more natural way to define the trig functions is using the unit circle. because you run into issues with the triangle approach because you usually define the triangle approach using a right triangle. But the problem is, like, what if you want to take the sine of an, and so that only allows you to take the sine, cosine, and tangent of acute angles. But what if you want to take the sine, cosine, or tangent of an obtuse angle? Well, you can't really do that. You have to do some more, you have to do extra work. It's not as natural. But with the unit circle approach, you can take it's clear that you can, the way the trig functions are defined, you can take sine, cosine, or tangent of any angle. It doesn't matter. Any angle you want, and it will work out. So a little bit more natural to do it that way. All right. So that's all I wanted from that. So let's go back to this document, OneNote document, and work on another problem. So we want to, so that was example one. Now we're doing example two. And we want to solve the following triangle. So I'm going to try it here. So it looks something like this. And so we have, this angle right here is labeled A. This angle is labeled C. And we're told that this is a 20-degree angle and this is a 25-degree angle. And then this angle is called B, but it's unknown. And then this side right here, the one across from side C, well, it's length C and it's given as 80.4. And then this side is A, this side is B, and these are unknown. So to solve this triangle, we need to figure out angle B and sides A and B. But we can figure out angle B pretty easily because we're going to use, we're given two angles and we can use that fundamental fact about triangles that which states that the sum of their angles is 180 degrees. So to find angle B, we just take 180 degrees and subtract from it the sum of the two other angles. And if you do that, you get a 135-degree angle. All right, so now let's write down the law of sines and figure out how it can help us to solve the other sides. So we got these, the law of sines states the following. Sine of C over C. And so what we're given is this side right here. And so, and we want to find A and B. So what we're going to do is we're going to take this and set it equal to this because everything, we know angle C and we know side C. And then we're going to take this and then set it equal to this. So we're going to have like these two separate equations we're going to use. So sine of A over A is equal, we're going to set equal to this. And we want to solve for this A right here. And if you do that, I'm not going to go through the algebra. I sort of already did that with the other example. If you do that, you find that A is equal to C times sine of A over sine of C. And everything on the right-hand side of this equation is known. So we're told that C is equal to 80.4. And then we have sine of 20 degrees over sine of 25 degrees. And I guess you can plug this in your calculator. Yeah, we don't know sine of the 20-degree and 25-degree angles are not angles that are known actually. So this will be approximately 65.1. So A is approximately 65.1. And then similarly, we can solve for side B. And in this case, we're going to take this whole thing and set it equal to that. And we know this angle here, we know this angle, and we know this side, so that means we can solve for B. So similarly, we're gonna have sine of B over B is equal to sine of C over C. And if you do the algebra, you'll see that B is equal to C times sine of B over sine of C, and then you can plug in data, so it's 80.4 times sine of 135 degrees over sine of 25 degrees, and that is approximately 134.5, which you get from plugging in the calculator. All right, so I think that's basically really all we need from law of sines 6.4. So I'm gonna just stop. I'm gonna pause this for a moment, and then we'll pick up in 6.6 on the law of cosines. Okay, so now we're gonna learn about the law of cosines. So let me share my screen. So for this one, there's gonna be a case. So the reason why we need the law of cosines because there are going to be cases where the law of sines is not going to be helpful. So let's um so let's say the law of sines can't always be applied in solving in a triangle. And remember, solving a triangle is kind of odd language. We just mean that I give you some information. I give you a triangle with some information on the sides and maybe some angles, and you want to deduce or figure out or compute the other sides and other angles. So it can't always be applied in solving a triangle. So let's recall the law of sines. It says sine over a. Sine of a over a is equal to sine of b over b is equal to sine of c and over c. So for example, here's an example of a triangle you cannot solve using the law of sines. So I'm going to give you an example, and let's try to see why. So we'll say that this is C, this is A, and we're going to actually return to this example after I introduce the law of cosines, because the law of cosines is going to allow us to solve this triangle. Let's say this is 82.4 degrees. This is 388, this side. So this would be B, side B. This would be side A is equal to 212. And then this is C, this side's unknown. So the idea is we want to figure out angle A, angle B, and then side C based on this three pieces of information. Well, now we can't use the fact that the sum of the three angles equals 180 degrees because we only have one angle. It's not going to help us determine the other angles. So right away we can't use that fact, which was kind of crucial in using the law of sines. But now, okay, so any equation you try to set up using these three equations is just there's not going to be enough information. So let's actually substitute in what we do know. So we don't know the angle A, but we know the side length is 212, and it's equal to sine of B. We don't know angle B, but we do know the length of B, which is 388. And then we have sine of C, which we do know, and that's 82.4 degrees over C. So now just imagine all the possible equations you could set up using these three equations. And you can see that there's just no way to solve for any one for one of the three unknowns. So like you could set this equal to this. The problem is you'll have two unknowns. You'll have this A here and this C here. So the best you can do is write C in terms of sine A or sine A in terms of C, but you won't actually get a relationship. So then another alternative is to set this equal to this. But again, you're going to have two unknowns. Sine of A is equal to sine of B. And the best you can do is solve for one in terms of the other. And then the last thing you could do is you could take this equation and set it equal to this one. And again, you still have two unknowns. So this triangle, um, you can't using the law of sines, you can't solve for it. So you might think, well, there's just no possible way to solve it at all. And that's where you'd be wrong because you can use the law of cosines. And it's okay to be wrong in mathematics, by the way. It's perfectly fine. Um, So let me write down the law of cosines and then I think we can prove it. It's a little bit more complicated. It's not terrible. So this is another theorem. This is the law of cosines, and then we'll look at a couple examples. So the law of sines says that, sorry, the law of sines says that in a triangle, A, B, C, we have the following equations that hold. We have this first one says a squared is equal to b squared plus c squared minus 2 oops, it's not working again. I don't know why. Uh, let's see if this will work. All right, this is working. Don't know why. Okay, let's start over, I guess. So all right, actually just uh deleted everything I did. All right, well, anyways, that was hopefully recording. Yeah, I think this is recording. So just deleted what I wrote. But anyways, so let's write down the law of um cosines. So it says that in any triangle, A, B, C, we have the following three equations hold. We have that the following three equations hold. So the first says that A squared is equal to B squared plus C squared minus 2BC times cosine, so BC, and maybe I'll put a dot there so to distinguish those, times cosine of A. And then we have B squared is equal to A squared plus C squared minus 2AC dot cosine of B. And these might look complicated at first, but you'll be able to see a pattern emerge. So it'll be easy to memorize them. And I'll try to explain it in a bit. The last one says that c squared is equal to a squared plus b squared minus um, 2 ab cosine of c. These are actually, I want to point out, this is like a generalization of the Pythagorean theorem, actually. So you have like, let's see, please don't freeze again. So this is like a generalization. Pythagorean theorem. And you could see, you can kind of see that. So like you have like, say C is your hypotenuse and A and B are either the lengths of the legs. You have like, here's the Pythagorean theorem, but then you have like this extra term right here. And this term takes into this extra term takes into account that it's like a correction, it's like an error term. Takes into account that A B, C might not be a right triangle. So let's look at what it says special case of a right triangle. Special case of right triangle. Of course, I haven't proven this yet. I'm going to prove it in a moment. But what happens? Let's like apply this to the right triangle case. So in this case, our triangle looks something like this. This side will be C, and then this side, I guess, is A, and then this is B. This will be angle B, A. Uh, actually, let's see. No, I don't want to set it up that way. It's freezing again. I don't know why this computer is moving so slowly. Uh, yeah, I mislabeled this, and now I want to fix this. There we go. I want to say this is ridiculous. This is A, this is B, and then so this is all right. Hold on. All right, hopefully this move a bit faster now. All right, so this will be, let's see. Okay. This is A, this is B. And so this angle right here is going to be angle C, but it's a 90-degree angle because we're in a right triangle. So in that case, um, so the last equation, so this is C, and it's a 90-degree angle. We know for a fact it's a 90-degree angle because we're assuming we're in a right triangle. Last equation becomes, so it's this equation that's now disappeared. This last equation right here. So let's copy this down, and you'll see that it simplifies a bit. So it's C squared is equal to A squared plus B squared minus 2 AB cosine of C. But now C we know is a 90-degree angle. So C is either, you can think of it as a 90-degree angle or the same thing as pi over 2, right? If you're thinking about unit circle, whichever way, doesn't matter. And so now this is like what I call right here is like, you can think about this as like an error term. It's like your your triangle isn't quite, so remember the Pythagorean theorem holds that is a squared plus b squared equals c squared if your triangle is a right triangle. And so what this the law of cosine essentially says is like, if you don't have a right triangle, the Pythagorean theorem doesn't quite hold. You have like this error here. So it's like measuring how far, like this error term right here basically measures how far your given triangle is from being a right triangle. So your triangle might not be, it might be close to being a right triangle, and so you have to like take into account the fact that it's just a little bit off from being a right triangle. So you have to subtract it off. So that's why this looks so much like the Pythagorean theorem. But now when your triangle just is a right triangle, there is no error. And so we should see that this error term actually just completely cancels out and we get the Pythagorean theorem. And that's exactly what happens. Because cosine of 90 degrees or cosine of pi over 2 is 0. So this whole thing right here is 0. When you have when you have an honest to God right triangle, there is no error term, and so the Pythagorean theorem should hold, and it does. So this is like a generalization of the Pythagorean theorem. So how do you kind of remember this? Well, you really only need to memorize one. because if you notice, the other ones are kind of just like rearrangements. Okay, so here's how I try to remember it. So here's the one right here, this thing right here. So let's say just focus on this first one. So on the left hand side you have a, so the cosine should be a, and then you need the equation has to involve the other sides of the triangle. So that's where you get the b squared and the c squared. And then the only instance of A on the right hand side is this cosine A, and so you have this BC here. So you because you have the BC and you have the B here and the C here. And if you look at the next equation, it's literally almost the same thing as this first one, but just rearranged a little bit. Now on the left hand side we have B, and of course in the third one we have C. So it's just like you can get another way of saying this is like these two equations right here are permutations of the first ones, like rearrangements. So the second one right here is you have now B on the right hand side, left hand side. So you have to have the A and the C, the other remaining sides on the other side. So and they're going to square them, and then the coefficient, and then because B is on the left hand side, you're taking the cosine of B here, and then the coefficients of this cosine are going to be your 2A because you have this A here matches with this A, this C matches with this C, and finally, like you have this last equation. Now you have C on the left-hand side, so it's gonna be cosine C, and then the right-hand side has to involve the other sides of the triangle, so you're gonna have A squared and B squared, and that means you have the AB right here. So yeah, they seem kind of complicated at first, but really they're if you can just memorize the pattern of this first one, these other two are just more or less just rearrangements of the first one. All right, so let's try to let's use the law of sines to figure out how to solve that triangle, which the law, or sorry, now that we have the law of cosines, let's try to solve that example I presented at the beginning, which you couldn't solve using the law of sines. So the law of sines, well, you couldn't use that to solve the triangle I drew at the beginning. So let's redraw this triangle and figure out if the law of sines, cosines can help. So the triangle is something like this. This is example one. It's a whole example. It's like you're this excavator and you're going to build a tunnel to the through the mountain, but who cares? So you can, if you really want to see it, you can go to the example in the book and it's sort of like an application. But the point is, like, you're given this triangle and you know one side is 388. You're given this angle here. It's going to be 82.4 degrees. And you're given this side here, 212. So we have these two angles right here that are unknown, and we have this side, little c, is known, is unknown. So this is going to be B, and this is going to be A. So now, we what we want to figure out is we want to figure out C, and we want to figure out length C and angles A and B. So the equation we should use is that last one I drew, that last one I wrote, sorry, because this is the one that involves C, okay? And in fact, we know A, we know B, and we know angle C. So we have everything we need to figure out C. So we can say by law of cosines, we have that C squared is equal to A squared plus B squared minus 2AB times cosine of C. So always write down the formulas in their general form before plugging in numbers because it's going to help you memorize them. So that I always get in the habit of doing this. And that's why I know what these equations look like because I write them down in their general form first. So this is what we want to solve for. And we actually have everything on the right hand side is given. So we can actually say c squared is equal to 212 squared. So 200, whoops. Come on. Yeah, maybe I need to like run a cleaning app on this thing because this is ridiculous. It's not even that this computer's not even that old. It's honestly it's Microsoft and Bill Gates is the devil basically, so shouldn't even buy Microsoft anymore. That was too political of me to say, of course. Maybe I'll get canceled. All right, anyways. Um So we have 212 squared. So we have, this is a, so we have a squared, and then we have this b over here. So it's going to be plus 388 squared. Whoops. Squared minus 2ab. So 2 times 212 times 388, and then cosine of angle C, which is 82.4. So that's how you plug this in. And now I guess you just use a calculator. Oh, so C squared is approximately going to be, it's this horrible number, 17370.2367. And then now if you take a square root, it's going to be approximately the square root of this number, which is, I guess, 416.8. All right, so now we're going to look at another example. And again, um, the sine law of sines is not going to be helpful. This is going to be an example where you're given all three side lengths, no angles. And so if you look at the law of sines, you'll see that they won't be helpful. So this is example 2, and we're giving a triangle that looks something like this. So I have A, B, and then C, and then we have B is equal to 8, A is equal to 5, and then C is equal to 12. So we don't know any of these angles, but we know all the side lengths. So if you, as I said, if you, let's just write this down and see why it's not going to be helpful. So sine of A over A, which in this case is 5, sine of B over B, which is 8 in this case, is equal to sine of C over C, which is 12. And again, if you take this and set it equal to that, two unknowns. You can't solve for either sine A or sine B. Set this equal to this. Again, two unknowns. You can't solve for either sine A or sine B. And if you set this equal to this, two unknowns. You can't. So you need the law of uh, cosine. So let's write those down. So we have these three equations. A squared is equal to B squared plus C squared minus 2A, sorry, not A. So let's just kind of waiting here. Right, whatever. A squared is equal to B squared plus C squared minus 2BC cosine of A. And then you have B squared is equal to A squared plus C squared minus 2AC times cosine of B. And then you have C squared is equal to A squared plus B squared minus 2 AB cosine of C. So in all of these, we're given these numbers right here, the A, B, and C. So we had all of those. So what we want to do is just solve for cosine A, cosine B, and cosine C. So if you do that, so let's look at the first one. I won't, this is the unknown, the angle. So if you do that, I won't go through all the algebra, but you solve for cosine A, you get that it's equal to B squared plus C squared minus A squared over 2BC. And now you can plug everything in. You get A squared plus 12 squared minus 5 squared over 2 times 8 times 12. That's going to give you, actually, it gives you exactly 183 over 192. And now to get cosine A, you just apply the inverse function. So that's going to imply that angle A is equal to cosine inverse of 183 over 192, and you plug that into your calculator. And I guess that is not equal, but approximately 18 degrees. And you can do the same thing. So you could take this second equation here, if it decides to show up. There, this is ridiculous. So I'm just gonna, oh, here we go. You have this second equation here. You can solve for cosine B. And then, yeah, I'm gonna just pull the book up now because this is being ridiculous, this computer. So you can solve for cosine B, you get this, and then um, you get that cosine B is equal to this. So you can find the angle by taking the inverse, plugging that into your calculator. So cosine inverse of 0.875. And then you can do the same thing for C. So actually, yeah, so technically, right, as they're saying in this paragraph, technically you can use the law of cosines to get angle C by doing the exact same algebra and procedure and then taking the cosine inverse of what you found, which is that right there. But you can also use the fact that if you know angle A from here and then angle B, you can use the fact that the sum of the angles on a triangle is 180 degrees to get angle C. You just subtract the two from 180, the sum of the two. So that's another way. So, but it's like it doesn't hurt to use the law of cosines. Um, let's see. There might be. We're not going to do that. I don't care about that. All right. There's just was one last example. I guess we'll go through. Right here. So now this is side angle side. So it looks like what we're given is this side right here, this side, and then this angle. So that you're given an angle, and then you're given two sides and the angle between them. So again, if you write down the law of sines, you get sine A over A. So the sine B over B is equal to sine C over C. So you're given, right, let's just plug what we're given in. It's always a good idea to write down the sine law of sines first, because if you can use it, definitely it's a lot easier to use. So you would definitely want to use this if possible. Um, so it's always good to write this down first. But if not, then you know you need to use the law of sines. So we're given B is equal to 10.5, and then sine of C, we don't know C, angle C. We know side C is 18, 0. So again, so to solve this triangle, you need to find side A, and then the two angles. So, but the problem is, you can see that if you try to set up um, any equation involving A or sine B or sine C, you're going to have two unknowns. So it's just not going to work. So you definitely need to use law of cosines. So yeah, we have this triangle here with given this angle and these two sides, and this angle is between the two sides. So you want to solve for the other ones. So for example, you can use the first equation of the law of cosines. So you have this one right here is a squared equals b squared plus c squared minus 2ab cosine A. And we're given B and C, and we're given the angle A. So this works out. So it's just a simple plug. You plug it in and then use the calculator. And then to get the remaining two angles, you do the same sort of manipulation, same sort of algebra that I actually skipped over, but say the one that I imagined, the one that I told you to kind of imagine in your head, I guess. You can solve for cosine B and cosine C in a similar way. And then do a simple calculation right here. So this is in the book. These problems they're not terribly difficult to do. It's just a matter of memorizing the law of sines and cosines. And once you've written them down a couple times in the course of solving these problems, you see that they're not that hard to memorize. These are just more or less like plug and chug. Um, so actually one thing I just realized is I did not prove the law of cosines. So let's just look at that really quickly. I won't write things down because my computer's acting up. So here's the statement. You have any triangle, A, B, and C, and the claim is that these three equations hold. And so I think we're just going to prove one, and then, yeah, I think we're just going to prove one of the equations, and then the rest are like follow similarly. So the idea is you start with a triangle, and then you could just put a coordinate system around it. So just assume that this vertex A, where this angle A is, just assume it's the origin for simplicity. And then if that's the case, then so if because this side length right here is C, this coordinate must be C comma 0. And then, but what about this right here? What's the coordinates for this point? So we're basically like putting our triangle sort of in standard position in a sense. So just like start with the triangle and then build the coordinate system around it so that one of the vertices of the triangle is just the origin of your coordinate system. And then because this length is C, this point right here must be C0. But what about this point right here? Can we work that out? Um, so let's see. Why is that the case? Well, I guess what you could do is let's see. So you can drop this down. I didn't actually look through this proof beforehand. Get this right triangle. And then, oh, okay, so this is angle A, and then this must be 180 minus A. So you have this right triangle. Okay, so now we want to figure out the X, we want to figure out the length of this right here, and then this length right here. So we have this triangle. So let's like imagine that we like take this right triangle out right here. Okay, so this angle right here is going to be 180 degrees minus A. We know that this hypotenuse is B, and then we want to figure out um, this length right here, and then this length right here. So, and we want to express it in terms of these angles in this known sides. So, first of all, let's call this, say, X, and then let's call this Y, because these are going to give us our X and Y coordinates, and they're going to eventually give us this point here. So let's just call them X and Y. So we know that, for example, sine of 180 degrees minus A is equal to the opposite y over b the opposite divided by the hypotenuse, so y over b, and then that's going to imply that the y coordinate is equal to b times sine of 180 degrees minus A. But this is actually sine of 180 degrees minus A. We saw that earlier. Actually, it just ends up being sine of A. Sine of A. So that's why the y coordinate is b times sine of A. Okay. So now the x coordinate is going to be, let's figure out what the x coordinate is. So now we're going to use the cosine of that angle. So we have cosine of 180 degrees minus A is going to be equal to the adjacent x over the hypotenuse over b. And then you can solve for x, and you'll find that x is equal to b cosine of 180 degrees minus A. And then this simplifies again to just cosine of A. So that's why the x and y coordinates of this point, the x coordinate and y coordinate is b cosine A and then b sine A. All right, so how does that help? So let's kind of let's figure out what they're doing here. So to prove the law of sines, as I said, you're going to place the triangle so that the angles at the origin, as shown over here. So that I already explained. It's just easy to do it that way. And then the coordinates of the vertices B and C are C0, and then this other coordinate, this other point, which we just figured out. We figured out those coordinates using this right triangle nonsense. Now, so what we can do is we can use the distance formula. Let's see, what are they doing here? Okay, this is kind of dumb actually, I think. Let me see what they're doing. So this length right here is so this looks more like Pythagorean theorem because like look at if you drop this line down here and then you consider this whole length right here and then this whole length right here, that's a right triangle also. So I don't right, so let's write out that whole triangle then. So there's like this bigger right triangle, right? And then we have that this is gonna be what are the points to this? B cosine A. And then this is oh yeah, B sine A. And somewhere right here is like 0, 0, and then this is right here is C 0. So that implies that this point right here is gonna be um it's gonna be B C cosine A comma 0 because it's on the x-axis. So and then this length right here, this is gonna be A. So the hypotenuse, so basically what we have is A squared. So we want the length of this line right here, and then this line here. So, so it's going to be, I guess it would just be, oh yeah, so it's going to be, that's really weird actually, because they have negatives in there. We should be able to get this. So the length of this line right here is just going to be b squared. Oh, it's going to be the y coordinate squared because that's the length right there. Plus, and now that's going to be some possibly negative number. It's going to be definitely be a negative number. Oh, so that's why I want to subtract it, I think, right? Because then it'll make it positive. So it's going to be C minus B cosine of A. So this right here, squared, is the length, is this length, and then combined with this length right here. It gives you this whole length. So A squared to be equal to B squared sine A squared plus when you FOIL that out, you should get C squared minus 2AC times cosine of A, and then plus B squared times cosine of A, cosine squared of A. All right, so now we have this B sine A squared and then B cosine C squared. So you can put those together and factor. So, oh yeah, this is right. And then what you'll get is sine squared A plus cosine squared A plus C squared minus 2AC times cosine of A. Okay, this is close. This almost looks like the law of cosines, the first equation, right? Now we just need to use the fact that if sine A squared plus cosine squared A is equal to 1, that's like one of the Pythagorean identities. So if you plug in 1, if you replace that by 1, you get your b squared times 1, which is just b squared plus c squared minus 2ac times cosine of a. And that's exactly the first equation. So that proves, so you can see this is exactly the law of this first equation right here. And then you could just repeat the process by, it gets a little trickier because like we drop down this. So I guess what you would want to do is maybe drop down to get the other ones, you would want to start at this vertex and then drop these two lines to get this other right triangle. I'm not sure. It should basically be the kind of the same sort of reasoning and argument, but this at least proves this one. We proved that one at least. So, what's the idea then? So the idea is you we first needed to figure out these coordinates right here. We didn't know what they were, but if you form this right triangle and then like kind of like remove this triangle right here and put it right here and do some just basic trigonometry, you can figure out the y coordinate, which we did, and then you can figure out the x coordinate, which we did right here. And so now we know the x and y coordinates of this vertex right here. And then because we dropped this line down right here, we have this actually, we actually have a bigger right triangle. So I drew it down here. So like the origin was here, there's this point to the left, and then there's this point to the right. And so the original triangle, I guess, would be something like, actually, maybe I'll use a different color, just so you can kind of see where the original triangle is. The one we started with, I'll put it in a dotted line right here. So I just kind of removed the triangle from the picture so I could like get the features of the triangle I needed. Um, and then from here we could use Pythagorean theorem to relate the lengths of all the sides. So the hypotenuse squared is going to be the length of this side squared plus the length of this side squared. Well, this side squared is just b sine a squared. Because remember the y coordinate gives you the height from the x-axis, and this right here is just the height from the x-axis. Plus, I need to add this length and then this length right here. And that's going to be c. So the length from here to this point is just c. And then I got to subtract off the length from here to here because it's negative. I want to make it positive because I'm basically adding these two lengths. So you got to, I mean, what you could do is you could actually add this and put in, which I don't want to do. I need this. Hopefully, it's clear why I have to subtract this off because I want to make it positive because I want to make this a length and then I want to add it to this length to get the length of get the length of one of the sides of this big right triangle. And then you just once you use the Pythagorean theorem right here, you just you just kind of expand. You square this term and then you expand this and then FOIL and then you put this term with this term. So you basically have a b squared that you can factor out from this term and this term. And so you have b squared and then this thing in parentheses and then plus the rest of the stuff. Well, this thing right here is just 1 by the Pythagorean identity. So you have b squared plus c squared minus 2ac times cosine a. And that proves this first identity right here. And the other ones can get using a similar argument. So that's all. So I'm going to stop sharing now. That's all we have and then we're actually completely done. There's no new material. So that's it.